Hi guys, welcome to my lecture on applications of second order ODEs to mechanical vibration. This is the 11th lecture for the semester. And essentially what I'm going to do today is to look at how a spring mass system can be reduced to a second order differential equation. Right? Now spring mass systems are very important mechanical systems. They are a prototype for suspension systems in vehicles, as well as the mechanism by which most doors operate. Right, and so we're going to look at the basic setup, and then we'll just derive the differential equation from this result, and then go ahead to look at the different kinds of oscillations or vibrations that can come out of this setup. All right. So just to illustrate what a spring mass system is. Right. So as the name implies, we have a setup where there is a spring. So let this be our spring. And attached to this spring is some mass, some object of mass m. Right. And so this happens on one side of the system. And then on the other side of the system, there is a damping mechanism called a dashpot. And the dashpot is typically filled with fluid or some kind of material that can damp a very highly viscous fluid that can damp oscillations. Okay, so we have a dashpot here, and then our spring has a rod that extends into the dashpot. Okay. Now, what happens is that the spring, the object is initially in some rest position, indicated here in red, and it is pulled towards the right. Okay, so this is my rest position, right? The object is pulled towards the right, and so we'll consider this direction the positive direction. And once the object is pulled towards the right, this rod is pushed into the dashpot. So this is our dashpot here. Okay. So the object is the rod is pushed into the dashpot. Now the force in the spring now pushes the object towards the left, or tries to pull the object back to its rest position. And then by so doing, the rod has to move through the fluid in the dashpot, and it encounters some kind of resistance, right, in that fluid. Just like you would encounter resistance if you were moving your hand through, oil, right, versus through water, you're going to feel some resistance. So as this rod is moving up and down in this dashpot, it feels some resistance from the fluid inside. And so the spring, once you pull the object away from its rest position, the spring attempts to pull it back, right? And then in so doing, it may even compress the spring. In other words, push it much closer to the edge here. And then again, the force in the spring tries to push the object back towards the right. And so the object keeps moving from right to left, from right to left, from right to left, as it's also being damped out by this dashpot here. And so the motion eventually slows down. Okay, so what we want to consider is a function, x of t, that can predict the motion of the object. Okay, so x of t will be the position at any time of the object. All right, now we're going to look at two cases. We'll look at a case where there is no damping mechanism here, so the dashpot is absent. and the edge, this end of the spring is free, it's just moving in air. Even though air itself poses some kind of resistance, we're going to assume that it's negligible if the mass is very heavy. And so if there's no dashpot, then we're assuming that this rod is just moving freely without any resistance. And so we'll look at what kind of motion we can expect from the object in such a scenario. And then we'll also look at a scenario where there is a dashpot mechanism that would act as some kind of damping factor to kind of slow down the oscillation of the object. Okay. Now, like I said, this is a very typical system. If you've ever, opened, a door to a mall or even to your kitchen, right? There are different things that can happen depending on the mechanism by which the door is designed. Okay. So there are certain doors that if you push them, they kind of swing back and forth. They swing back and forth until eventually they are, they damp down and then eventually come back to their original rest position, right? There are other doors that if you swing them, they just gradually move slowly and then they stop back at their original position. Okay, so all these mechanisms are controlled by some kind of a spring-mass system, a Spring-Mass-Dashpot system that is attached to the door, and that is able to control the force with which the door closes, or whether or not the door is going to swing back and forth and how long that's going to happen, right? So this is a very important mechanism. It's also a similar mechanism that is in the suspension systems in vehicles, so that if you are driving on the bumpy road, the springs that attach the tires to the body can kind of withhold some amount of shock. If you have a very bad vehicle, then you're going to be vibrating for some time before it actually damps down, right? So this is a very important system, and being able to come up with a solution in terms of one that describes the position at any time t will allow us to make predictions about when we can expect the oscillations to stop. We can actually describe the oscillations, right? We can talk about what is the frequency of the oscillations, what is the amplitude of the oscillations, what is the period of the oscillations, and then we can talk about how long it takes until you can get some maximum displacement from your rest position. So all these are important parameters that we can examine once we have a solution for the position of this object at any time t. So what governs, what physical principle? Because remember that anytime we are trying to find the differential equation to mimic a physical process, we are thinking about what physical principle kind of governs this process, right? And because this is a motion of an object under some kind of external force, we can apply Newton's second law of motion. That tells us that the force, the result of the total force on an object that drives its motion should be equal to the mass of the object times the acceleration of the object. Okay, where the acceleration is really the second derivative of position. So this is x prime prime of t, since x is the position of the object at any time t, right? And so my force is really mx prime prime, right? Now this force here is the sum total of all the forces that are acting on this mass here, this object, right? We call this the resultant force. Okay, so we want to take a survey of all the forces that are at play here, right? Of course, the first force that is very important in this motion is the spring force. Now, there are two kinds of forces that the spring imposes on the object, right? The first force is once the spring is stretched, the spring wants to come back to its original, its original form, right? So there is a tendency of the spring to want to bring the system back to, kind of some kind of an equilibrium state or a stable state. That is called the restoring force of the spring, right? And it happens when you try to stretch the spring or when you compress it. So again, if you have a spring and you push it much closer together than it previously was, there's a force that builds up in your hands that wants to kind of bring it back to its original position, right? Hopefully everyone has had an experience playing with some kind of spring, and so you can either get a force that wants to push you back to rest when you compress or when you stretch. Any kind of deformation of the spring generates a force that wants to bring you back to your original position. So we'll call this the restoring force in the spring. And one thing we know from observation is that the magnitude of this restoring force depends on just how much you stretch or how much you compress the spring, right? And so it is directly proportional to the amount of displacement that you subject the spring to, right? So if we think of the displacement as our x, then because the force, for example, if you stretch the object, the force is always trying to bring you back in the opposite direction to the displacement that you imposed. We will think of this force as having a negative sign. So I'll call this Fs, right? And this force will be, since it's directly proportional to the displacement, it will be minus some constant. Let's call this constant K, times the degree of displacement, which is x of t in this case, right? So since x is measuring the displacement from rest, it is exactly how much deformation we have subjected the spring to, right? So this is how we're going to model our spring force, minus kx, where my k is positive. Okay. Now the second kind of force is the damping force from the dashpot. Okay. Now this force is a result of the motion of the rod that is attached to the object as it moves through the fluid. Okay, and it is really a resistance that the fluid, the resistance that the fluid poses to movement, right? And that kind of resistance can be quantified in some form of friction, right? Because the fluid really doesn't want to be displaced, and so you are forcing it to be displaced by moving this rod up and down. Okay, so that is some kind of frictional force. And that frictional force is directly proportional to the velocity at which you are moving the rod up and down in the dashboard. So it's not as related to how far you move the rod in the dashboard as in how fast you move it. Okay, so a very typical example is when you rub your hands together, there is a resistance to that motion that is created by you forcing your palms against each other, right? Now, the faster you rub your hands together, the more heat you generate in your palms, right? So as you rub it very, very fast, you realize that you generate a lot of heat. That heat is a result of that. It's some kind of transfer of energy from that friction that is being created, right? And so that heat is greater the faster you rub your hands together. It's not really dependent on how far you rub your hands, but it's more dependent on how fast you rub your hands together. Okay, and so generally friction has some relationship to velocity and not displacement. And so we're going to model this damping force, let's call it FR, right? And again, also in this case with the dashpot, the force is also opposing the motion of the dashpot. So if this rod is trying to move up, the resistance tries to keep it down, so it's in the opposite direction. So this force, we can think of it as minus c times the velocity, which is x prime of t. Okay, now if there is no other force that is acting on this object, we are going to ignore the effect of gravity for the moment, because we are kind of suspending this mass with a spring, and so we, whatever is happening in terms of gravity is happening uniformly. And we can, for the moment, ignore the effect of gravity. And so we're only going to consider the spring force and the damping force as the main forces that are going to contribute to the motion, the left and right motion of this object. Okay. All right, so my f is really minus kx minus cx prime. Okay, and so if I replace this f here, I have minus kx minus cx prime is mx prime prime. And if I move everything to the right hand side, I have mx prime prime plus cx prime plus kx is equal to 0. And notice that we have here a second order linear homogeneous differential equation with constant coefficients. Okay, so this is a model that we can definitely solve, right? As long as we know if we know the mass of the object, and if we know this friction coefficient C or damping coefficient C, and if we know the spring constant K, right, then we've completely determined this differential equation. If we have an initial condition on the initial displacement and the initial velocity, right, we have an initial value problem that we can find a particular solution to, and that particular solution will govern the motion of the spring or the motion of the object, as it is driven by the spring and resisted by this dashpot. All right, so next we're going to look at the two cases of interest to us at this moment. The first case, we are going to assume that there is no dashpot, which means that, so case 1, we're going to assume that C is 0, right? And then that will give us, what is called an undamped system. And then in the case 2, we're going to assume that C is some positive number, and that will give us a damped system. Okay. Now, all of these two cases, we are assuming that, again, the only forces that are driving this motion are the spring force and the dashpot system. Okay. Now, if it happens that there is another force, for example, some kind of electric motor that may be attached to the object that is also driving it to the left and to the right, then there's an extra force F here. Okay, and so that would give us a non-homogeneous second order differential equation. Okay, which we can also solve, because now we have methods to solve non-homogeneous second order equations with constant coefficients. Right? When there is another force outside of the spring force and the damping force, then we call this a forced system. We'll take examples of this later on. Then in the case of course, when there's no force, then we say that we have a free system. So this is a free system. All right. So under the forced system, you can also have a forced damped system, forced undamped system. So all of these classifications can still be present there. So in retrospect, we can say that, well, we have two major systems. We have either we have a forced system or a free system, and if in either one of those categories, we can have a damped or we can have an undamped situation, right? But our focus for this lecture will be on the unforced or the free systems. Okay, so let's look at the first scenario where we have a free undamped motion of the object. All right, so again, our differential equation is mx prime prime plus cx prime plus kx equals 0. Right? If we have an undamped motion, it means that there is no dashpot present. Right? So my c is 0, and so my differential equation is mx prime prime plus kx is equal to 0. Okay, and what we want to do now is we want to understand the different kinds of motions that we can anticipate from this problem, and then we can look at how to measure certain quantities of interest, such as frequency, period, amplitude, and so on and so forth. And then we'll take some examples. All right, let's divide this equation through by the mass m, so that we can put this in standard form. Plus k over m, x is equal to 0. Right. And then let's call omega 0 squared k over m. Right. Now this k over m here is telling us the relative strength of the spring with respect to the mass. Okay. So it's basically giving us a measure of how strong the spring is given the mass of the object that we have. Right. So it's going to be an important quantity, going down the line. So this is relative strength of the spring, in a sense. We'll define this more formally later on. Okay, so that gives us an equation x prime prime plus omega naught squared. Let's just use w because I can't seem to write omega. So this is x prime prime plus w naught squared is equal to x is equal to 0. Right. Now, if we want to solve this for x of t, we can use the characteristic equation. So we have r squared plus w0 squared r is equal to 0, right? Which means that my r squared is minus w0 squared, and then my r is going to be plus or minus w0i. Right? And so I know that my solution to this homogeneous problem will be of the form e to the r t. Right? So we can use e to the w0 I t, which if we apply the Euler's formula is the cosine of w0 t plus I times the sine of w0 t. Right? So we know that both the real and imaginary parts are solutions, and so my x of t, the general solution, will be c1 cosine of w0 t plus c2 sine of w0 t. So this is the nature of the movement of the object, right? And so one thing to immediately notice is that if there is no dashpot, then this object is just going to vibrate forever, right? Because the cosine and the sine, these are both periodic functions, and so they're going to keep moving up and down, up and down, up and down for all time. So this is not going to stop, right? Which is not a very realistic situation, because we know that even if you displace an object attached to a spring in air, eventually the object is going to slow down. That is because of air resistance. But if we were to do the same experiment in a vacuum, right, then we would expect this to be the scenario where the object just is displaced forever, in a sinusoidal fashion. Okay, so this is our motion, and a couple of things that we are interested in here. Right. We would like to ask the question, one, what is the amplitude, right, of this motion? The amplitude is the maximum deviation from rest. Okay. So think about what is a period. Right. The period is the time it takes to go through one oscillation. Right? So if you think about the mass beginning from a rest position, is displaced, some distance, initial distance x0, it moves back, and then it keeps going back and forth, right? So the period, essentially, we are looking at, when it's going to come back to the same position, how long it takes for it to come back to the same position that it was before. That's the period. And this is usually measured in seconds. And then we want to think about what the frequency is. Right? The frequency is the number of oscillations per second, right? Or of course 1/, the period, and this is measured in hertz. Right? There's another kind of frequency that we're going to be interested in. It's called the circular frequency. This is more related to angular frequency for those of you who have studied physics. And it's just looking at, a rotation, and thinking about this as some kind of rotation instead of just a linear movement. Right? The circular frequency is going to always be W0, which is this parameter here. Okay, so once you find your solution, you can almost always pick out your circular frequency. And then the other thing we're going to be interested in is a time lag. The time lag, you can think of that as the time it takes, for you to reach your maximum displacement from the rest position. Okay, and that will become clearer as we go on. So you think of it as some kind of a shift in the graph of your function. Okay. All right. Now, to be able to accurately pick out all of these parameters, it is important to combine the solution into just a single trigonometric function. So either a cosine or a sine. It just makes it a lot easier to identify these parameters. So for example, as it is now, it is unclear what the amplitude is, right? Because we have, the cosine curve has some amplitude, the sine curve has its own amplitude, C2. And so, in terms of a superposition of the two curves, the cosine and the sine, it's unclear what the effective amplitude would be. Right? So all these things we'll have to, we have to measure, and for convenience, we will combine this into a single trigonometric function. And so to do that, we are going to set, let's call A our amplitude. We're going to define our amplitude as the square root of C1 squared plus C2 squared. Okay, so that I can now I can write my x of t. So this is the amplitude. I can write my x of t as A into C1 over A cosine of W0t plus C2 over A sine of W0t. Okay. And then next, we are going to let the cosine of some angle alpha be C1 over A, and the sine of the same angle alpha be C2 over A. Okay. So that the x of t can now be expressed as A times the cosine of alpha, the cosine of W0t, plus the sine of alpha. So my alpha is some angle between 0 and 2 pi. So I have sine of alpha, and then I have sine of W0t. Okay, now if you remember your trig identities, this can be expressed as the cosine of W0t minus alpha. Okay, And so now I've been able to express my displacement function as a single trigonometric function, cosine. Okay, so then it's very clear here that the maximum value of the cosine of this function here is going to be a. So that my amplitude is going to be a. My period, since the original period of the cosine is 2 pi, and we have somehow scaled this cosine by w0, my period is going to be 2 pi over w0. My frequency in hertz will be w0 over 2 pi. This will be in hertz. Of course, my circular frequency is w0. This is in radians per second. Like I said, it's some kind of angular frequency. And then my time lag, we will define as alpha over w0. Okay, so it's a total shift in the function. So you can, if you write this as a cosine w0 out, you have t minus alpha over w0. Then it's clear that this function, this cosine function, has been shifted to the right by alpha over w0. That is your time lag. Okay. All right. So these are the important parameters that we want to extract from this motion of the objects, and these parameters would completely determine what is going on here, and we can measure these values and make we can predict all of these parameters here. Okay, so that's all for the free undamped motion. So what if we introduce damping, right? What if we introduce a dashpot? How does that affect the oscillation? Okay, so again, notice that this system, as we have set it up, is going to vibrate forever, right? Because we keep going to, like as a cosine function, we can just sketch the graph quickly. So the cosine originally should have started from 0, so cosine of 0 should be 1, but because this has been shifted by alpha over w0, we may end up, instead of having 1 here, we may have 1, after a while here. Right. And so we could have that this function is behaving something like that. And then it keeps going on, and this is going to repeat itself. This is my time lag, alpha over w0. Right. Of course, my period is just the time it takes to repeat myself, and all the other parameters you can determine from here. So this is my time axis, and this is my x-axis, x of t. Okay, so let's look at the damped scenario. So once again, my differential equation is mx prime prime plus cx prime plus kx is equal to 0. Right. Now, if I assume that my c is no longer 0, then I can express this in standard form, dividing through by m. I have c over m x prime plus k over m x is equal to 0. Okay. Now let's call c over m, let's call that 2p. The reason will become clear in a moment. And then we're going to continue to call k over m w0 squared. Right. So now we can write this as x prime prime plus 2p x prime plus w0 squared x is equal to 0. And our goal is to find a solution to this equation given some initial conditions. All right, so if we can derive the characteristic equation, it's going to be r squared plus 2pr plus w0 squared is equal to 0. And if we want to find the roots of this characteristic equation, it's going to be minus 2p plus or minus the square root of 4p squared minus 4w0 squared divided by 2p. 2. And so if we simplify that, we have minus p plus or minus. If we factor out a 4, so that's going to give us a 2 outside, which is going to divide this 2. So we have the square root of p squared minus w0 squared. Right. So these are, we have two roots, r1 being minus p plus the square root of p squared minus w0 squared, and r2 being minus p minus the square root of p squared minus w0 squared. Okay. So there are a couple of things that can happen here in terms of cases. Case 1. If we assume that p squared is greater than w0 squared, then we know that we have two real distinct roots, right? So in that case, let's call p squared minus w0 squared. Let's call that w1. Let's call that w1 squared. And so that my r1 is really minus p plus w1, and my r2 is going to be minus p minus w1. Right. And so one of my y1, in this case my x1, right, x1 of t should be e to the r1t, which is e to the minus p plus w1t, which is e to the minus pt times e to the w1t. And then my x2 is my second linearly independent solution, e to the r2t, which is e to the minus pt times e to the minus w1t. Right? So that my general solution is C1 so my general solution is e to the minus pt. I have C1 e to the w1t plus C2 e to the minus w1t. And this is the kind of motion that I can expect if p squared is greater than w0 squared. Okay. So what do we observe with this kind of motion? Okay. So notice that in this scenario we don't have any kind of sinusoidal motion here, right? Where we oscillate. There is no oscillation here. These are all exponential functions. And we know that exponential functions are either monotonic increasing or monotonic decreasing. So there is no oscillation, there is no vibration here. Right? There's no vibration here, and what happens though is that so notice that from here w1 squared is definitely going to be smaller than p squared. Okay, so in terms of this function, this term here is going to dominate the behavior of this function over time, because p is much greater than w1. Right? And so because p is positive and this is e to the minus pt, we can expect that my x of t over time will decay. will approach 0 as t approaches infinity. Okay. And it will do this without any kind of oscillation. Okay, so as you get some visual of that, this is our t-axis, this is our x-axis. We may start from some, original displacement, but what happens is that the mass is just going to move closer and closer to its rest position, which is 0 displacement, right? Even though it's never going to really get there, it's going to get closer and closer and closer to that rest position. Okay. Now, because of the fact that we don't have any oscillations in this case, and the object just, it just kind of gradually decays to its rest position, we term this case as an overdamped case. Right. And this is because the assumption of p squared being greater than W0 squared. Remember that P has to do with the damping factor or the damping coefficient, and W has to do with the spring constant. So saying that P squared is greater than W0 squared is really somehow inferring that the resistance from the damping is greater than the spring. The resistance force from the dashboard is greater than the spring force. Right. So in that case, it's going to overwhelm the spring, and the spring is not going to be able to pull the object past its rest position. Okay. So that is why we are seeing this gradual decay to rest position. This is because there's more damping than there is, the force from the spring that would have been able to move this object, left and right. So that's an overdamped case. Case 2. Right, we can assume that P squared equals W0 squared, which means that we have about the same level of damping from the dashboard as we have from the spring in terms of spring force. Right, and so what happens in that case? Then we get repeated roots. So R1 is just going to be minus P, right, and it's going to be the same as R2. So in that case, we can expect a general solution of the form C1 e to the minus pt, right, plus C2. We need a linearly independent solution, so t minus pt, if you recall this. Right. So that becomes the kind of motion that we are going to, and we can anticipate. We can simplify this. We can factor out an e to the minus pt, right, and then we have a C1 plus C2t. Okay, so this is also non-oscillatory, so there's no vibration here or oscillation because we don't see any sinusoids, cosine or sines flying around. But what distinguishes this case from the overdamped case is the fact that we can actually, so notice that in the overdamped case, there's no way that this term here is going to ever be 0, right? So this object is never going to go past its rest position. But in this scenario, we can actually imagine a case where C1 plus C2t will be 0, right? And so in that case, we can expect the object in this case to actually potentially cross its rest position, right, and then come back. So visually, we can imagine a situation like this. So this is x and this is t, and if we start from this point here, right, we can imagine a situation where we actually cross, but then eventually, because of the exponent, we will have to somehow go back to rest, right, because of this term here, which is eventually going to dominate whatever is going on there. right? And we can calculate the time when we actually cross our rest position, right? So we can set C1 plus C2 equal T, C1 plus C2T to be equal to 0, and find out, well, when the time is exactly minus C1 over C2, right, we would have crossed the rest position, right? We would have crossed the rest position, and then eventually we're going to make our way back to the rest position. Okay. 0 here. So this is called the critically damped case. Because there is some critical point where we actually cross the rest position. Okay, and again, you can imagine, you know, a door where, you know, if you swing it open, it kind of closes and goes past, you know, its rest position, and then eventually it's going to, you know, go back to its rest position. It's the kind of system that is going on here. So that is our critically damped position. And then finally, the last case, look at. So case 3, let's consider the case where now you have more, so the spring is much stronger. So let's say P squared is less than W0 squared, right? So here my spring is much stronger than the damping resistance. Okay, so that we can expect that the spring will overwhelm in whatever damping is present in the dashpot. Right? So if that happens, then let's set, let's call this minus W1 squared, right? So that in that case, I have two roots. My first root is I have minus P, you know, plus W1I, right? And my second root is minus P minus W1I. And so my my general solution, it's just one of my linearly independent solutions, e to the R1t, becomes e to the minus pt cosine of W1t plus sine W1t. And so my general solution, x of t, is going to be C1 e to the minus pt cosine W1t plus C2 e to the minus pt sine W1t, which we can simplify, factor out an e to the minus pt. We have C1, the cosine of W1t plus C2, the sine of W1t. Okay. So that becomes the motion that we can expect. Right here. So that my x of t, my general solution is C1. That's not what I want to say. E to the minus pt. I have C1 cosine W1t plus C2 sine of W1t. So this is a very interesting kind of motion here, right? So notice that you have a sinusoidal component, and then you have a damping component, right? Because just remember that this P here is positive. Okay. So this suggests that, you know, the object is oscillatory, so there is some kind of vibration. But then the vibration does not persist because of this damping factor here. That eventually, if you allow the process to go long enough, because the cosine and the sine just have a magnitude of 1, maximum, you know, value of 1, eventually this exponential is going to overcome this oscillation here, and then it's going to just draw everything down to 0. Right. So one can expect an oscillation of this form. So that we start from some, at 0, we have some displacement from the origin, we fall, and then we come back up, but we don't go quite as far as we did initially. We go back down, we don't go quite as far, and so eventually there is some, damping in the oscillations, and then eventually we just go towards 0. Right. So this is called the under damped case. Under damped because here we are assuming that the spring force is much stronger than the damping from the dashpot, and so we are able to see some kind of oscillation that will come from the motion of the spring. Now another very interesting thing to note here is that because of the damping, we really do not have a periodic motion, in the sense that the function never really repeats itself, right? Because by the time it comes around, its value has already been reduced. Okay, so unlike the undamped situation where we had it oscillating as a cosine function which was periodic, here because of the damping factor, you don't have periodic motion. So your values are never really repeated. So there are a couple of non-traditional things going on here. Right. First of all, we don't have a fixed amplitude because the object's maximum displacement from rest changes with time. And then secondly, there isn't a fixed period. There isn't actually even a period because you don't ever return to the same position twice. And so the frequency also is not, the notion of frequency is also not very, very well defined, right? But in any case, we can still talk about, a period-like, motion. We can talk about, something that is like frequency, and we call those the pseudo period and the pseudo frequency, right? So we would still like to kind of write this as a single trigonometric function so that we can extract out what the amplitude is, because at this point in time, we still have a C1 and a C2 here, and it's not immediately clear what the amplitude would be, or how exactly what the maximum displacement would look like over time. So just like we did with the with the underdamped case, we can write this oscillating part here as a single trig function, so that we have we have AE to the minus PT cosine of W1T minus alpha, right, where my A is the square root of C1 squared plus C2 squared, and my alpha, of course, is the angle for which, so alpha is the angle for which the cosine of alpha, right, is C1 over A, and the sine of alpha is C2 over A. Okay, so that we can determine what alpha is, and so we can write our our motion in this way. And from that, we can extract what we'll call the time varying amplitude. So my time varying amplitude is A e to the minus pt. That is governing these points here, these maximum points here. We can derive what is called the pseudo frequency, pseudo period, which is not really a period because we don't repeat ourselves, but it's a, like period, so pseudo period, which is 2 pi over W1. W1 is a circular frequency. Again, this is not really, clean frequency because, we don't really have a periodic motion here. So the textbook also gives the option of referring to this as the pseudo frequency. Right, and that is of course W1, and this is in radians per second. And then of course you can still pick out the time lag, which is alpha over W1. So these are the parameters that we are going to discuss with regards to this underdamped situation. All right. Okay. Now, in practice, you don't need to, remember what p squared is, what w naught squared is, and all these classifications. All you need to do is to be able to set up the differential equation and then solve it. So you just need to find out what your m is, what your c is, what your k is, right? Throw that into a differential equation, find out what your initial conditions are, and then you can just solve your initial value problem, right? And then out of that initial value problem will come some, displacement function that you can then, write as a single trigonometric function and then extract out the parameters that we need. All right, so let's take some examples. A body with mass of 0.5 kg is attached to the end of a spring that is stretched 2 meters by a force of 100 newtons. It is set in motion with initial position x0 equals 1. So we have some information about initial position and initial velocity of -5 meters per second. We also know that the mass of the object is 0.5 kg. Now there's a note here that the velocity is negative because the object is displaced to the right, but then it moves to the left. So the velocity is actually opposite to the direction of displacement. All right, so the question is to find the position function of the body as well as the amplitude, the frequency, the period of oscillation, and the time lag of the motion. This is frequency in hertz, which is 1 over period. Okay. If I want the circular frequency, I will say circular frequency. So just so that you are not confused. All right. So we know that generally the spring mass system is governed by the differential equation mx prime prime plus cx prime plus kx equals 0. Because here there is no mention of an external force, so we know that there is no extra force here. So this is a homogeneous equation. We are also not given any information about a damping effect, so that implies that my c has to be 0. So I'm really looking at mx prime prime plus kx equals 0 as my differential equation. Okay. Now I already know what the m is. My mass is 0.5 kg. So what I need is my spring constant. Okay. And to find the spring constant, we are given some information here. We are told that the spring stretches 2 meters by a force of 100 newtons. All right. Now, since we know that the force is directly proportional to the displacement, it means that the constant of proportionality is going to be the force over the displacement, which is here 100 newtons over 2, right, which is 50 newtons per meter. Okay, so that is our spring constant K, and so we can write down our differential equation as 1/2 x prime prime plus 50x equals to 0. If we standardize it, we have x prime prime plus 100x is equal to 0. And then we can find a general solution to this. We have initial conditions that x at 0 is 1 and x prime at 0 is -5, right? And so we can find a particular solution to the initial value problem. And that will tell us the motion of the body over time. All right, so let's go ahead and solve this. We have x prime prime plus 100x equals 0. Characteristic equation is r squared plus 100 is equal to 0. And so my r squared, right, that is minus 100. So my r is plus or minus 10i. Right. And so we know that, my solutions are the form e to the rt. So this is e to the 10i t, which is cosine of 10t plus I sine of 10t. And so my general solution, x of t, is c1 cosine of 10t plus c2 sine of 10t. Okay. And so clearly, this displacement is going to oscillate forever. All right, so this is clearly a motion without any kind of damping. Right. And to be able to find out, the amplitude, frequency, and all these parameters, we'll have to find the particular solution to this equation. So we need C1 and C2. We can go ahead and find the derivative. So we can use the velocity condition. So my derivative is minus 10 C1 sine of 10t plus 10 C2 cosine of 10t. Okay. So I know that my x of 0 should be 0, and this implies that my C1 is 1. My x prime of 0 should be -5, and that implies that my C2 is minus 0.5. And so my particular solution is cosine of 10t minus 1/2 the sine of 10t. Okay, so to pick out our amplitude, we're going to combine this into a single trig function. So we're going to set our amplitude A to be the square root of 1 plus 1/2 squared. Which is square root of 5/2. So then we can write our x of t as the square root of 5 on 2 out. We can factor that out. We get 2 over square root of 5 cosine 10t minus 1 over the square root of 5 sine 10t. All right, so if we let the cosine of alpha be 2 over the square root of 5 and the sine of alpha to be minus 1 over square root of 5, then we have that our x of t is square root of 5 over 2. Right, this is 2 over, this is cosine of alpha, cosine of 10t plus sine of alpha, sine of 10t. So if we combine this, we get the square root of 5 over 2. We have the cosine of 10t minus alpha. So we can extract a few parameters already. Right. Our amplitude is going to be the square root of 5 over 2. Right. Our period is supposed to be 2 pi over omega 0. This is 2 pi over 10. So this is pi over 5. And then our frequency in hertz is, of course, 5 over pi hertz. Period is in seconds. Now we need the time lag. Right? We can also extract that. We were not asked to do this, but we can always find that the circular frequency. This is quite straightforward. By definition, this is 10. This is in radians per second. And so to find alpha, right, we're going to use the fact that cosine of alpha is positive and the sine of alpha is negative, right, to figure out what quadrant alpha is in. And then we'll use, just some trigonometric properties to figure out what alpha is. Okay, so remember your trig, that if the cosine is positive and the sine is negative, then it means that the terminal side of our angle is in the fourth quadrant. And so this is really my angle alpha here. Okay. And since my cosine of alpha is 2 over root 5, my hypotenuse is root 5, and my x side is 2, my sine is minus 1 over root 5. So this is what I have. And I can, my alpha, if I call this acute angle here theta, my alpha is 2 pi minus theta, right? And theta is just going to be the inverse tangent of 1 over 2, where I ignore the sign of the y component here. So this gives me an alpha of 5.81954, right? And so now I can define my time lag as alpha over omega 0, which is 5.81954 over 10. So this is 0.58195 seconds. So what this time lag is saying is that it's going to take 0.5 or 0.6 seconds before my object is displaced, is displaced by square root of 5 over 2 meters from its rest position, which is the amplitude. Right. So that, again, the time lag is the delay in reaching your maximum displacement from the origin. Right. We don't expect that the initial displacement, which is 1, is going to be the maximum displacement. Okay, it's very rarely the case. So that's what the time lag tells us. And that's it. That's all the information that we want out of this problem. We've been able to. So you can write your particular solution. If you want to complete this, this is cosine of 10t minus 0. Alpha is 5.81954. And that's it. Okay, so by far the most crucial part is just you being comfortable with this trig aspect where you have to find alpha, right? And I just recommend you don't have to. The textbook gives you some formulas. You don't have to memorize any of those formulas. You just have to remember your trig, find out where the angle is, alpha is where its terminal side lies, and you can use the sine of the cosine and the sine to determine that. Determine your reference angle, and then just find your reference angle, and then use the relevant relationship to the complete revolution 2 pi to determine what your alpha is. Right? So you don't have to memorize any formulas here. Okay, so let's look at an example where there is some degree of damping. All right. So we have the same mass and spring system, except that now we have introduced a damping effect. So we have a dashpot that provides 1 Newton of resistance for each meter per second of velocity. All right. So again, the general equation for the spring mass system is mx prime prime plus cx prime plus kx is equal to 0 for the free system. Right. We already know that our m is 0.5 kilograms. We know that our k is 50 newtons from the previous problem. Right. So we just need to determine the value of this friction coefficient or the damping coefficient c. Okay. Now we're going to use the fact that the damping force is proportional to the velocity, right? Which means that the constant c is the ratio of the damping force over the velocity, right? Initial velocity or whatever speed that we are looking at here. Let's use v for the velocity. And so in this case, I know that my dashpot provides 1 Newton of resistance for a velocity of 1 meter per second. So my c is 1. Okay. And so my differential equation is again 1 over 2 x prime prime plus x prime plus 50 x is equal to 0. And we have the same initial conditions, that initial displacement is 1 meter, and then my initial speed is -5 meters per second. Right. So that is our initial value problem. which we are going to solve. Okay, so again, we'll put this in standard form. So this is x prime prime multiplying through by 2 plus 100x 0. And then our characteristic equation is r squared plus 2r plus 100 equals 0. If we use a quadratic formula, right, we're going to get imaginary or complex roots, and it will be -1 plus or minus the square root of 99i, right? Which means that my x of t, right, will be c1 e to the minus t cosine of root 99t plus c2 e to the minus t, the sine of the square root of 99t. Right, and we can write this more compactly as e to the minus t. C1 cosine of the square root of 99t plus C2 the sine of the square root of 99t. Okay, so we need to determine C1 and C2 using our initial conditions. So we need the derivative of my position, which is minus e to the minus t, C1 cosine of root 99t plus C2 sine of root 99t. And then we have plus e to the minus t minus the square root of 99, C1 sine of root 99t plus the square root of 99, C2 the cosine of root 99t. So if we apply the initial conditions, x of 0 is supposed to be 1, which implies that C1 is 1. And then x prime of 0 is supposed to be minus 5, which implies that C2 is minus 4 over square root of 99. And so my position function is now e to the minus t. Right, my C1 is 1, so this is cosine the square root of 99t minus (4 over the square root of 99 sine of the square root of 99t. Okay. All right, so the next thing is to combine this into a single trigonometric function. All right, so we're going to define a to be the square root of 1 plus minus 4 over root 99, which comes out to be the square root of 115 over the square root of 99. And so my position is now e to the minus t. If I factor out square root of 115 over the square root of 99, what we have is square root of 99 over square root of 115, the cosine of the square root of 99t minus, we have 4 over the square root of 115 times the sine of the square root of 99t. So if we let alpha be some angle between 0 and 2 pi, and set the cosine of alpha to be the square root of 99 over the square root of 115, and we set the sine of alpha to be minus 4 over the square root of 115, then we can write our x of t as the square root of 115 over the square root of 99 e to the minus t times the cosine of the square root of 99t minus alpha. Okay. So what remains is to find alpha. And so again, we're going to use knowledge from trig. First, figure out which quadrant alpha is in. Again, the cosine is positive and the sine is negative, which tells us that we are in the fourth quadrant. And my alpha, is an angle. Is that angle there? Let theta be our reference angle. And then we know that if our hypotenuse is a square root of 115, then we have the square root of 99 here, so that the cosine will be the ratio we have, and then we have a minus 4 here to get the sine. Right. So I'm just using, opposite of a hypotenuse, adjacent of a hypotenuse to put these values here. So I know that my alpha is 2 pi minus theta, right? Which is 2 pi minus the inverse tangent of 4 over the square root of 99, which is going to give me an angle between 0 and pi over 2. And so that comes down to 5.90094. Right? And so we can write down our displacement function more precisely. .90094. And so now we can extract all the information that we need. Our time varying amplitude again, this is time varying because of the effect of the exponential. It's just going to be the square root of 115 over the square root of 99 e to the minus t. This is going to change continuously with time. Our pseudo period is going to be 2 pi over omega 1, which is just 2 pi over the square root of 99. So we have what? 2 pi root of 99 over 99. And then the pseudo frequency which is really the typical circular frequency in radians per second, is going to be omega 1, right? Which is the square root of 99 rad per second. And then our time lag, I can also write that down. Our time lag is alpha over omega 1. So this is 5.90094 over the square root of 99, which is approximately 0.594 31 seconds. So again, we still have a delay in this system where it takes about 0.5 seconds for it to hit, in this case, not really maximum displacement, because you know, the amplitude keeps changing with time. So you know, the maximum displacement keeps decreasing, right? So again, the time lag here is it's not as formal as we would have in the undamped situation, but we would still like to, you know, think of it as a time lag, as some kind of shift, you know, in the intrinsic trigonometric function, ignoring for a moment the effect of the damping, so the effect of the exponential factor. All right, so these are the, you have homework problems like this, and you can use these ideas here to find out the parameters that are required in your homework. Next, we're going to talk about Laplace transforms to solve constant coefficient non-homogeneous equations, or both homogeneous and non-homogeneous equations. And then as we make that discussion, we will introduce some examples with forced oscillation, where we have some kind of electric motor or something that is driving the object to move. But at this point in time, I just want to focus on these free oscillations, just to give you a head start. Okay. All right, guys. Here are some practice problems for you to try. And if you have any questions, we can talk about this on Thursday. All right. Enjoy the rest of your day. And don't forget to take the quiz. Okay. Bye.